In this third part of lecture 1, we're going to look into methods that we can use to forecast demand. We can divide the forecasting methods into qualitative and quantitative methods. In this course, we're going to look only into the quantitative methods. And these ones can be subdivided into time series and causal methods. What we're going to do in this video is to look very briefly into 3 methods for each one of these subdivisions. Let's start with time series. So time series projections are for sure the most widely used methods by airlines, especially for small airlines that do not have such a data analytics capability. They are simple, and that's why they are widely used. They establish a direct relation between traffic and time. So time is the only factor that explains the evolution of demand. And what is assumed is what happened in the past will happen in the same way in the future. So all factors that influence the variation of demand in the past will stay in the same way in the future. And so we can just project the evolution that we observe in the past into the future. 2 typical approaches for these time series projections are the linear trend method and the average rate of growth method or exponential trend. The first one assumes that to a given demand, D0, we add every year as the same amount of new demand, which we call here with a constant, we call it var. So every year we add, for instance, 200 new passengers to the market that we are trying to forecast. On the other hand, the exponential trend method assumes that there is a rate which is constant. So this is the AAG, or annual average growth, in the expression at the bottom. And what we assume is that there is a percentage, so a ratio, that is fixed over the time. So to the demand that is given, D0, we add every year 1 plus 2% or 3%. So if you understand this method, you're going to see that the growth won't be linear, but will be exponential, because 2% every year will result in a higher absolute amount of passengers that we are adding to the market per year. How do we calibrate this method? So we need to calibrate the AAG and the var from the previous method. So how do we do that? The most typical approach is the ordinary least squares, where we try to plot our predictions, given the factor that one value of the factor that we are trying to calibrate. And we compare those predictions with the data points that we do have from the past. So, for instance, we can see in this figure, if we have the data points in red, and we have our prediction given a specific calibration value, we have a difference between those values and at a given moment, and we're trying to minimize this difference, which we call residual values. These are represented here in green. And what we are doing is just obtaining the best beta, the calibration variable that we are trying to calibrate, by summing all this difference to the power of 2. And 2, so we can eliminate the factors that some of these differences are positive and negative. And if we use this sum of residual values, we determine a coefficient of determination, which is the R square, which will tell us if our prediction, if our function, calibrated function, is good or not. So ideally, we would like to be close to 1 to say that we have a good function. There are some more advanced time series methods, like the autoregressive moving average. So here in this method, what we assume is that the demand that we're going to observe in a given year t is influenced by what we have as a demand in t minus 1, time t minus 1, eventually time t minus 2, time t minus 3. So this is the blue part, so the autoregressive model part of the ARMA technique. And we also assume that there is a linear relation over time on our errors, on the what is called the white noise used here as a parameter epsilon. And this is the moving average model, and it's expressed there in red. So if you combine both, you do have the ARMA technique, and you can calibrate this function, so the parameters alpha and beta, by using again the ordinary least squares or a maximum likelihood estimations. I'll leave up to you to explore the maximum likelihood estimations. Okay, but these are methods, what we observed so far are methods that only relate demand with time. But it's easy to understand that there are factors that cause the variation on the demand that we have observed in the past. So one of them, which is really well known for air transport, is the relation between demand and GDP, let's say the economical power of the countries in which the trips are generated. And this is a not so recent graphic, but still is very evident from this graph that there is indeed a relation between the GDP per capita of several countries and the amount of trips they have generated in those countries. So it is fair to assume that these factors like GDP can influence demand. And there are many factors that can influence demand, like the fare of the ticket that you are buying, the travel time that will take you to go from your origin to destination, the type of service. But also, besides GDP, other economical factors like the purchase power of the society in the country, fuel prices, political drivers, but also at the individual level, the reasoning of traveling, what is the purpose, leisure or business, what are the passenger characteristics, the age, the size of household, and so far and so forth. What we can do with these factors is to combine them in what we call regression models or econometric models, where we put all these factors into relation towards a single explanatory, a single dependent variable, which is our demand. And we can assume multiple formulas. So we see here more a multiplication formula, and here more a sum of all these relations between factors. And we have to calibrate all these A, B, C, and D calibration parameters. And again, we use the ordinary least squares or the maximum likelihood. A specific version of these econometric methods is the gravity model. It's widely used in long-haul transportation demand forecasts, not only for air transport, but in general transportation problems. And the reason being that it's easy to explain, it's easy to apply, and doesn't require so much data in principle. So it's very suitable for new routes. And this gravity model, like the name says, comes from the gravity theory from Newton, in which two bodies attract each other depending on the size or the mass of each body and the distance between themselves. And for us, we say that the demand between two points, origin and destination, depends on, let's say, the population or the GDP of each one of the points, and inversely proportional to the distance between those points, and distance could be measured in time, money, or any other factor. And we have to calibrate this beta and k in this expression, and again we use the ordinary least square, which we can do by linearizing this function by using logarithms in both sides of the expression. How do we formulate and compute the parameters that we want to calibrate in this function? These functions in general, causal methods. So first we have to start by identifying and selecting the factors. Identifying by understanding what could be important in that specific market, but also what is available in terms of data. And these are the independent or explanatory variables that we're going to use in our methods. Then we have to test and understand what could be the function that we are going to use, so the formulation of the function. So how are we going to relate these factors with the demand? And this can again be done by knowing the market that we are working on. So if it's a growing market, maybe we want to go for something that use the power functions or use multiplication between factors, because those are the formulations that allows us to model a faster growth. While if we are dealing with stable markets, maybe we want to go for a linear expression, because those are more stable. In any case, we can try multiple variations. We can calibrate and compare which one produced the better fit to the data. We also need to analyze the results at a deeper level, not only in terms of coefficient of better fit, but also in terms of each one of the factors that we are using. So are they significant, statistically significant or not? Do they represent a logic that we expect? Like, for instance, if GDP has a negative sign related to demand, it sounds strange, because we know that as GDP grows, we also should expect demand to grow. So if it's not logic, if it's not statistically significant, or the coefficients that we are determining for a specific factor, maybe we have to eliminate those factors or factor from our expression and recompute again and recalibrate it again. Once we have done with this process, we need to validate, test with the results with some extra data if possible, and only then we are at the point of using the method for forecasting future values. In the causal methods, we can also include machine learning methods. They are special methods, so they are methods that, on the contrary of the traditional ones, where we do have input data, we specify the algorithm and then we try to calibrate the algorithm, and then we produce the output. In machine learning, we look more into matching the input and output, asking the computer to get an algorithm for us. We do all use, of course, some structures, some techniques to define which type of algorithm we are looking for, but it's up to the computer to define the formulation of our algorithm. And we can use many techniques. There are many available machine learning techniques. We're going to discuss here the rich regression and the random forest, but we can also have a look into neural networks or, for instance, gradient boosting algorithms, which combine a set of learning algorithms together. Let's then look into rich regression. So when should you use rich regression? Well, they are really useful for the situations where we have few data points. So when you do have less data points than the number of features that we are trying to use, then rich regression comes in hand. Also, they can be used in the case that you do have data that suffers from multicollinearity. So in the previous causal methods, we assume that the explanatory variables are independent. There is no relation between them. If that's not true, then perhaps we need to start looking into methods like rich regression. So what we do here with rich regression is to follow a regression method like the ones that we discussed before, the econometric methods. But when we calibrate our betas, our calibration parameters, we use a cost function that penalizes those betas. And this is very convenient. So we do use the same residuals, so the square of the difference between what we observe and what we are estimating with the current version of our method. But then we have this lambda multiplied to the sum of the betas, because we want to mitigate the case that we have a very high beta just because of the case that we do have a few data points, and this will be a normal tendency. So we want to penalize to don't have this harmful effect in our method. You can know more about this method by following the link that I provide here in the slides. The other machine learning method that I would like to mention to you today is the random forest. So they are useful when, again, the data suffers from multicollinearity, but also when there is no linear dependence between your factors and your dependent variable, which is demand in our case. They are also very convenient in the case that you have missing values. So in some data samples, you don't have complete information. Random forests can deal with that very easily. And they can also deal with a large data set, so with high dimensionality, with multiple factors playing around at the same time. The idea is that you build your algorithm based on multiple decision trees. We're going to see in the next slide what is a decision tree, but the idea is that you have these trees which produce a result, and then you merge their estimations to produce a more accurate and stable prediction of the value that you are trying to predict. It is also good to know that it is easy with this method to understand what is the importance of different features or factors in your predictions, which is sometimes something very convenient. Again, I leave here a link to a video which can tell you more about random forests. So random forests, as I said, are a combination of decision trees, are a forest of decision trees. And here in this example that you see here a decision tree in which I'm trying to predict the demand based on factors like is it weekend or not, is it a Friday, does it depart before 10 a.m., is it the fare lower than a given amount. So I can use these factors to try to understand what should be the demand, and then it's up to the training of the algorithm to define which factor should be at the top, and then it's true or false. If it's true, you're going to look into the departure time, it was before or not before 10 a.m. If it's false, you look into Friday, is it Friday or not? And then you move lower in your tree until you get, so you start dividing in branches until you get to the end node, which tells you the value that you should get for your demand forecast. If you have many of these trees, thousands of these trees, then you can average the value obtained by all these trees. To avoid that you have a repetition of trees and an overfitting to a specific data that you use for training, you can use techniques like bootstrap, which is a method that divides your data in subsets in random, so you don't use the full data set, but you divide in parts, potentially with some repetitions. And feature pegging, which is a method that not for all trees considers all features that you provide to your training methods. So it means that some features will not be considered in some decision trees, and this force a random forest method to have different trees of different formats in the forecast of your demand. I leave you with a summary of all these methods with different aspects relevant for our demand forecasts, in which we can compare not only the time series projection methods and the causal methods that we analyze, but also two well-known qualitative methods. And you can see which ones are the best ones, for instance, to apply new routes or unstable markets, or which ones are more costly in terms of implementation. You can explore more about these online, but you can also come with questions to our Q&A sessions. I'll see you there. Bye-bye.